Hello, this lesson is going to be about max and min values. We'll just start out with just a simple picture to discuss. So, see something like that without any specifics about the x and y values. The major thing about the maximum and minimum values, obviously we're looking for maximum, we're looking for values that are bigger than all other values. We'll have two different distinctions, and for good reason. So first, you might look at, say, that point and say, well, that's not a maximum because there's a point here. So we're going to distinguish between absolute maximum values and local maximum values. A local maximum value will be defined as a value that is larger than the values near it, right? So, for example, if this is the x value of 2, well then at x value of 2, the function is higher than at all values around 2, right, at any neighborhood surrounding 2. And if you're thinking like, well, is it all values or is it just some values? As long as you are bigger than your neighbors, right, both your left and right side neighbors, then that can qualify you to be a local minimum or maximum. However, of course, if this is 8, f of 8, if we call this thing f of x, f of 8 is clearly the maximum value on the entire interval from 0 to 10. And then it looks like f of 10 would be the minimum value. Notice that that would be the absolute minimum value, and here would be a local minimum value. So we're going to distinguish between the two, and we'll have methods of finding both of them. You can see that the local min values are going to be, local min or max, I'm sorry, in this case local maximum values, will be at the top of the hills, right, at the top of a rounded hill, or at a peak in a function, something like that. We'll have a method for finding those, and if those don't turn out to be the highest, the only other option for highest and lowest values are the endpoints on the interval. And I think you can understand why, because let's say the function was just that. If I erase that piece, we're thinking as we go through this, well, that's the highest in its neighborhood, that's the lowest in its neighborhood, that's the highest in its neighborhood. So between these three values, you probably have located the absolute minimum or maximum. The only other option would be to see what happens all the way on the edge of an interval. And if you're thinking, why is that the only other option? Well, if there were another option somewhere in this interval where it was highest, it would have had to come back down, and another local would have been created, another local minimum or maximum. So we're going to have methods of finding tops of the hills and the bottoms of the valleys, the local mins and maxes, and then that'll allow us to at least see most of the time what the absolute min and max is. If we have functions such as this one, where it just so happens that the endpoint is the absolute maximum, absolute minimum, we'll have to go back through and just test the endpoints of the function. So again, we'll find the hills and valleys, and then we'll test the endpoints. An interesting thing that you can observe, if I just ignore the rest of this now, just looking at these relative minimum maximum values or local minimum and maximum values, is think about its derivative at the point. Obviously we just spent quite some time studying the derivative, but if you think about the tangent line to that point, and that point, you can tell they're clearly horizontal. So these all have a tangent line with slope 0. So effectively, what we're going to find out is, as long as we take our function, we take our equation, we take its derivative, and we find whenever it hits 0, we will have found the points where the function levels off, right? Or ceases to increase and then begins decreasing, or ceases to decrease and begins increasing. So in this case, you can see the function was increasing, 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 then it started heading down. So that when the derivative is 0, it'll tell us where that pivot happened. What we're going to do is, let's just do an example. a really simple example like the function x minus 5 squared plus 2. Hopefully you know exactly what this function looks like. It is, of course, its parent function is y equals x squared, a parabola, right? A quadratic function. This one particularly is shifted over 5 to the right and up 2. So if we were hunting for its minimum value, since we know it has a minimum value, since we already know it's parabolic, what we would do is we'd find the derivative. To find this derivative, we of course need to employ the chain rule. 2 times x minus 5 to the first times 1, and then the derivative of 2 is 0, so we can also say the derivative is 2x minus 10. Now what we'll do is we'll take 2x minus 10 and we will find when it equals 0. So if I just set this thing equal to 0, I would solve and I'd get x equals 5. And all that's going to tell us right now is that it's either a minimum or a maximum. But we know based on this graph that the graph is 1, 2, 3, 4, 5, 1, 2. The graph has its vertex right there. So I used a well-known function, obviously purposefully here. But we found the derivative, we set it equal to 0, and then we found the point. We call these things critical numbers. Okay, there's two ways to find critical numbers. And this is definitely something you should make note of. Critical numbers are defined as when f prime of c equals 0 or f prime of c is undefined. Then x equals c would provide you with a spot of a critical number. Now, we call them critical numbers just because, of course, they're going to be of interest to us. So the function either changes direction, hits its bottom, hits its top, etc. Now, you can tell here, this is going to be, in this function, this would be not only just the relative minimum or local minimum, but we would also call that thing an absolute minimum because it is absolutely the lowest this function goes on the entire real number line. If you were looking for an absolute maximum, you wouldn't find any here, or even a local maximum, because this thing doesn't turn back around. So now let's consider a function where we don't necessarily know ahead of time what the thing looks like. It might be good after you work with it to graph it. That function will be x cubed minus 3x squared plus 1. So the first thing is, since I don't know what this thing looks like, and actually let's examine it on the interval from -1/2 up to 4. Right, and you could also write this as -1/2 to 4. Either interval notation is acceptable. So if those are the x values, if we're considering that to be its domain, and we want to know, tell me the local minimums and maximum values, and then also tell me the absolute minimum and maximum on this interval. First thing is we have an extreme value theorem, and the extreme value theorem is an existence theorem. What I mean by that is the extreme value theorem guarantees you that if you have a continuous function on an interval, that on a closed interval, that you will attain a minimum and a maximum value, a highest and a lowest. I know it sounds very simplistic, but it's not going to tell you where they are, it's just going to tell you they exist. So now what we'll do is we will take the derivative, because the first thing I'm thinking is I want to find the hills and valleys. Derivative is 3x squared minus 6x, and then we set that thing equal to 0. And we solve and we get x equals 0 and x equals 2. So that's telling us clearly that something is happening at 0 and at 2. And also in our interval, if you think about the interval from -1/2 up to 4, 0 and 2 are obviously in the middle there, so that's a good thing that we found those two values, of course, in the middle. Now what we've got to worry about, is that one a hill or a valley? Is that one a hill or a valley? and what happens at -1/2 and what happens at 4. So what we'll do is we'll test all those points. We'll do f of -1/2, we'll do f of 0, we'll do f of 2, and then we'll also do f of 4. Notice I'm not doing f prime, right? F of -1/2, that says substitute -1/2 into the function. F of 0, that's a quick calculation. F of 2, that's 8. I get -3, and I'm just going to check my calculations. And then 1/2 is 1/8. Make sure I'm right here. Yes. Okay, so now you can see that these are the only 4 choices. You've got to pick, you know, and if I sketch the function, it'd be useful to do that. F of 0 is 1. Now this is a really rough picture. I'm not even going to scale it. -1/2 is 8. F of 2 is -3, and F of 4 is 17. So something like this is happening, right? And you know, the detail here isn't really important. We know that that's clearly the absolute minimum, right? This one's the absolute minimum, and this one's the absolute maximum. And so we took the derivative, we set it equal to 0, we found where the hills and valleys were. They were at 0 and 2, and it just so turned out that x value of 2 gave us a minimum of -3, and an x value of 4 gave us a maximum of 17. Okay, that should do it.